Regarding random variables, remember we started discussing single random variables and then moved on to discussing random vectors or multiple random variables. And here we are going to do the same. We have discussed random processes and now we can talk about multiple random processes because in research or in real life, we observe a lot of random processes that are related, and therefore it's usually crucial to be able to express or analyze their uh, common behavior or their joint behavior. So what we are going to do is not very different than what we have done earlier. We will just define again joint distributions. Okay, so in many cases, we need to analyze the relationship between multiple random processes. And here we have just two simple examples. The temperature in a city, it's a random process across time. And the rain amount, again, is across time. But these two, you see, are related. They are related to each other in certain aspects. They are affected by the same effects, and they, they, they sort of behave together based on some factors. Therefore, it makes sense to analyze them together. Or in communications engineering, for instance, you have the input and output of a communication system, and you also have the noise. You have three random processes here. You have the input, the output, and also the noise are all different random processes, and they interact together. So they have certain relationships. It would make sense to be able to analyze their relationship. Again, we are going to make use of joint distributions to describe their joint behavior. Nothing is new here. You just, for instance, sample X at T1, sample Y at T2. This is the joint CDF. Obviously, you can increase the number of samples X of T1, X of T2, X of T3, Y of T1, Y of T2, for instance. You have just 5 observations. Or you can have even more random processes. X of T1, X of T2, Y of T1, Y of T3, Z of T4, Z of T5, something like that. These are all just joint distributions. And what you are dealing with is, you can think of it as a random vector. Whatever we have done earlier regarding random vectors, they all apply here. But of course, you have this joint CDF here. From this, you can define joint PDFs. And if you have discrete valued random processes, you can also define joint PMFs if it is appropriate. And more samples can be defined similarly, as I have just mentioned. Another point is X of t and Y of t does not have to be the same type. One of them could be continuous time continuous value. The other can be discrete time continuous value, or one of them can be continuous time continuous value. The other can be discrete time discrete value. All of these possibilities are there. Okay, you have many scenarios that can arise in such situations. Now, when you have multiple random processes, we can define cross statistics, as we have did with, for instance, covariance in random vectors. Now we can define cross correlation and cross covariance. Now, correlation in random vectors, of course, refers to functions of multiple random variables. But in the context of random processes, you have autocorrelation, where it is correlation between two samples from the same random process, but taken from potentially different time instants. But we also have what we call the cross correlation. So this defines correlation between the outcome of one random process taken at one time and the outcome of some other random process observed at some other time. Okay, X of T1, Y of T2. That is the definition. Okay, this is a very general definition. X and Y can be different. T1 and T2 can be different. And this is the definition of cross correlation. And similarly, we have the cross covariance. And this is just the central version, X of T1 minus the mean of X of T1, and Y of T2 minus mean of Y of T2. Multiply them, take the expectation, that is called cross covariance. Okay. Now, two very important definitions here, two concepts. We call X of t, Y of t orthogonal random processes if their cross correlation is zero, but for all possible T1, T2 pairs. If this is zero everywhere, okay? If that is the case, we call x of t and y of t orthogonal. In fact, this definition also um, is valid for random variables. If you have random variable x and random variable y, if their correlation is zero, we call them what? Not uncorrelated, because that is called covariance. We call them orthogonal. Okay, a little bit clumsy terminology, because, well, when correlation is zero, we don't call it uncorrelated. It's a bit weird, but when correlation is zero, we call them orthogonal. And this translates to random processes, but this is important for all possible T1, T2 pairs. Sometimes students get confused when, let's say, the cross correlation at t and t, the same time instant, is zero for all t values. This is not sufficient for calling them orthogonal. You have to make sure when you observe them at different time instants, they also have to be orthogonal. Okay? And similarly, when the cross covariance is zero, again, for all possible T1, T2 pairs, we call them uncorrelated random processes. Now, be careful about these definitions. The first one, first time instant, is for the first random process. The second one is for the second random process. So this indices and subscript orders, they are significant. It's not in autocorrelation and autocovariance, because this is defined in terms of a single random process. So if you exchange the time indices, it stays the same. Same with autocovariance. But when it comes to cross correlation and cross covariance, if you exchange time instants or if you exchange indices here, subscripts, then they are not the same. Be careful about it, because look at the definition. This is x of t1, y of t2. If you exchange the time indices, it becomes x of t1, y of t1, x of t2, y of t1. If you exchange the subscripts, it becomes y of t1, x of t2. Okay, so you have to be careful about these orders. But of course, if you change them together, okay, y of t2, x of t1, the order stays the same. So the equality is valid in this case. Have to be careful about these definitions.